Okay, thanks everybody, and please do pop those messages in the chat, and I'm happy to be interrupted if anybody has questions as we go. Okay, so as the title suggests, this talk is about quantum gravity and also information. And so my first picture here is sort of alluding to the famous story of Isaac Newton as he sat underneath a tree in Cambridge. So the story goes that an apple fell off the tree and he was wondering about gravity and the universe, and that was his moment of inspiration, as the story goes, to reach his universal law of gravitation. And on the other part of the picture, I'm depicting information in the form of binary digits, and that'll be something we come back to in the later part of the talk. So gravity is our most familiar force, and as Nick was just telling us, it's really very weak compared to the other forces that we understand in the fundamental description of nature. And Isaac Newton is credited with realizing that the force of gravity that we experience in our everyday life is the same force that controls the motion of stars and planets. And his idea was that gravity is a universally attractive force, which all matter attracts each other in a particular way. And you might have come across this in your study so far, or you might not, don't worry if you haven't, that the gravitational force, according to Newton's law, between any two massive objects is proportional to each of the masses and inversely proportional to the square of the distance between them. So that means the more heavy something is, the more massive something the two bodies are, the more they attract each other, but the more they separate, the weaker gravity gets. And it goes down as the square of the distance as it happens. And then there's some universal constant, and this is really a profound realization of Newton that this force of gravity that we're familiar with in everyday life is really universal and controls the motion of the universe on the bigger scales. And Newton's law is both simple, profound, but also very accurate. And it was accurate enough for NASA to use it to send astronauts to the moon, even though there was a more accurate theory that Newton's law was good enough. They didn't need anything better than that. And when NASA did send astronauts to the moon, they did their calculations using Newton's law of gravity. But as you might know, it's not the full story. So here I have somebody you probably recognize, Albert Einstein. And Einstein's theory of gravity is famously known as the general theory of relativity. It describes gravity in terms of the curvature of space and time. And the idea is that space and time, although they may seem to us that things travel in straight lines when they're not impacted on by forces, that actually we can describe gravity in terms of space and time being curved. So when we have a massive body such as the sun here, that we can think of it as making a curvature in the very fabric of space and time, which is depicted here as if it was weighing down on a rubber sheet. And this is a sort of very different explanation of the phenomenon of gravity, and it turned out to be remarkably accurate. And it's a very beautiful theory, and it was tested in its early days by a particular prediction. It predicted that light is bent by gravity, light feels the force of gravity in such a way that the amount of the bending of light, the force on the light, is twice as strong as Newton's theory predicted. And if you're studying physics at the moment and you're aware that every now and again you need to be careful about a factor of 2, you should know that quite a few times in the history of physics, a factor of 2 or something similar, a factor similar to 2, can be, make it or break it for an entire physical theory. And this was the first test of Einstein's general relativity when the observer is here at the bottom of the cartoon. Imagine yourself here on Earth, and people noticed that there was an opportunity to test at the time of a solar eclipse where a star appeared to be. So when we have a solar eclipse, the moon is blocking out the light of the sun that comes directly to us. And we can observe the apparent place, the position on the sky that a star happens to be, and compare it to where we know that the star really is based on all our other observations of that star. And when this was experimentally verified in the late 1910s, Einstein became an overnight world-famous superstar. And this is way before the days of Twitter and 24-hour news cycle. So there was a slight time delay until the papers got hold of it the next morning. But then it was all over the biggest newspapers in the world that Einstein had a new theory of gravity and that it had been make the prediction and been tested, and Einstein was suddenly a global superstar. Aside from that, general relativity, as well as being beautiful mathematical theory, it's also more accurate than Newton's theory, as I said, in such a way that it's necessary for the global positioning system to work accurately enough to get you down to the kind of precisions we're used to in our smartphones of being accurate up to about a few meters to 10 meters. And so here we have the global positioning system. This is known as triangulation. How your phone picks up your location is we have a large collection of satellites that are orbiting around the Earth. You may know about this, but your phone picks up bleeps from these satellites that to actually position yourself. Your phone doesn't send out any information. It just collects these signals that these satellites are bleeping out every now and again. And when it picks up 3 of them, often there's a little delay until it picks up all 3 when you open your maps. When it picks up 3 of them, it can measure your location by measuring the time differences between those bleeps. And so if you happen to be on the east coast of the US, as in this cartoon is, you'd be able to pick up your location from those satellites. And to do that accurately enough, we need general relativity. So it really is crucial in our everyday lives. However, we know that Einstein's general relativity is also not the full story of gravity. General relativity is what we call a classical theory, and that's a word which we use to mean that it doesn't contain quantum mechanics. And Nick was telling you all about quantum mechanics in the previous talk. So as you might have heard, I only came in and caught the last 10 minutes or so of Nick's talk. Quantum mechanics is the foundation of all of our theories of microscopic physics. And it also underlies all of electronics. And so actually your smartphone uses both quantum mechanics and general relativity. Quantum mechanics has been tested to very high precision at the Large Hadron Collider in CERN and in other experiments. So this is a photo of the Atlas experiment where often in these pictures you can see a sort of standard issue human. I'm not sure we have them there, but you can imagine each of these floors is about twice the size of a normal person. And so you can get a sense of the scale of this. There's 1, 2, 3, 4, 5 stories, 5 quite generous stories worth of buildings surrounding the Atlas Collider. So it's a pretty big machine. And this and other machines have tested quantum mechanics to incredibly high precision. So we're really very confident that it's the right basis for our fundamental description of the forces of nature. Let me just pause slightly to check that my time is there. Okay, great. Now, importantly, at the microscopic level, nature is probabilistic. What does that mean? Well, it means that when we do experiments in particle colliders, for instance, or more simple microscopic experiments, then typically there's a set of several possible different outcomes for which new particles are going to be produced and detected. And these outcomes are discrete. There's a set of possible particles. All of them can happen in principle, but these possible outcomes happen at different particular rates. And if you ask about any one individual event, then there's a percentage probability for each possible outcome. And we just know that by doing it many times and gathering statistics. One thing happens once, something else happens another time, but we can gather statistics which tell us about the probabilities for each thing to happen. And correspondingly, quantum mechanics is a probabilistic theory, as it has to be to reproduce these phenomena. And so a necessary feature, which is pretty obvious, is that all probabilities have to add up to 100% whenever we're thinking about all the possible things that can happen. And if we want to think about that as fractions, then all the probabilities have to add up to 1 at all times. And the fancy physics name for that is unitarity. Unitarity is just this feature that whatever we're predicting, that all the possible things have to add up to 1. That's what we always have for probabilities. Okay, so that's the sort of very basic ingredient of quantum mechanics. And so we're left with these fantastically successful, fantastically accurate theories of different aspects of fundamental physics. Quantum mechanics on the one hand, and general relativity on the other hand. And so ever since these two theories were developed in the early 20th century, people have been wondering, well, okay, great, let's just put them together, and then maybe we can have a unified fundamental theory of everything. That, you know, we can have a single description of all the laws of nature at the most fundamental level. That would be fantastic and amazingly satisfying. However, it's not quite so easy as that. It's not easy to combine these two theories into a single consistent theory, although we've made a lot of progress since the sort of 1920s or so. Because there's actually quite a big problem with that these two theories, on the face of it, seem to be incompatible with each other. And that's a problem. The sharpest expression of this incompatibility is found in the physics of black holes. And so let's take a look at that. Well, firstly, what do we know about black holes? Well, we've got quite a lot of evidence that they exist. What evidence do we have? Well, some of the best evidence up to about a little bit more than 8 years ago or so came from our own galaxy, the Milky Way galaxy, from people who were tracking, using observations, using telescopes, tracking the orbits of stars very near the center of the galaxy. And in this plot, we have the telescopes are pointing towards this very center of our galaxy. And the black hole, if it's there, is going to be very dark, so it's going to be very hard to see. But we can infer its existence by taking measurements over, you know, this quite a long period here, more than 20 years. And each of these dots represents the position of a star, which is making an orbit around the center of the galaxy. And by tracing together all those orbits, we can infer that there must be something very massive, extremely massive, right in the center. And some of the best constraints on this come from the orbits, which are the most extreme types of ellipses. So you can see these beautiful ellipses, and this pink and the green are highlighted here. But over on this side, you can see this very extreme, from our point of view, ellipse here, which is helping us see that somewhere right in the center here, there's got to be something very heavy. And that thing is very dark. It's very heavy. We're talking millions, at least millions of solar masses. And the only thing we possibly know that can be as heavy as that is, as massive as that object is, and as compact as is implied by all these orbits, the only thing we know is a black hole. More recently, since late 2015 and announced in early 2016, we have a whole different set of evidence, which comes from black holes out in the sky, which do a sort of very intricate dance of spiraling in as they're about to collide with each other. They spiral around each other, and that's these two here in the early phase. They're spiraling around, in a sort of death dance, if you like, where they're going to spiral around and merge. And in the moment of merging, they form something which is quite different from, looking like a sphere or anything near sphere. And there's a period then where after the merger, the black hole settles down in a phase known as ring down to a much bigger, to a bigger black hole, but a more spherical looking black hole. This is the cartoon, and this here is the signal that was actually observed in the two detectors, the two gravitational wave detectors in America. And so these, this signal, this characteristic signal of strain in gravitational waves corresponds first to this in-spiral phase, a big sort of energetic event of the merger, and then the black hole rings down. And these type of signals, again, the only thing we know that could possibly produce anything like that is a black hole. We now have quite a lot of data from these binary mergers as they're known. So merger means that they're merging together. Binary means that there are two of them to start with. And so here is 90 signals, all summarized in a single plot. And on the left, we have the less recent one. So the very first one I was just showing you is this very first event here, where the black holes are, let's say, around 30-ish solar masses, and they combine to make a black hole which is around 60 solar masses. So the mass of the objects are plotted here on the y-axis, and this is time on the x-axis. So these are the earliest detections. These are the most recent detections. And all of these blue dots represent black holes. So each column here is, in the first instance, two black holes which formed a bigger black hole. And that's what most of these, as we go along here. But as you might know, these gravitational wave detectors have also detected events which are down here at the bottom, where two neutron stars merged. And they formed something here which, if you can see carefully, is colored half orange, half blue. That's something which we're not 100% sure whether it's actually a neutron star or a black hole. And just for those of you who might not have seen it, a neutron star is a very dense, compact star, which is essentially when matter has been crushed such that essentially the whole star is made of neutrons. We're not quite sure what's quite on the inside there, but it's the last type of star, which is the densest possible type of star that we know of, that is the next thing to a black hole. So after a neutron star gets bigger than tries to get bigger than a certain size, the only thing we can say is we believe it forms a black hole. So that's why we have this intermediate mass range here where we're not quite sure about what's going on. But here we have, lots of fantastic evidence for black holes out in the sky. Okay, and finally, our third piece of evidence for the existence of black holes are these famous radio wave telescope images of the shadows of now two black holes by the Event Horizon Telescope. And one of these black holes was depicted in the leaflet for today's event, and the timetable for today's event. And I have two slightly different pictures. So on the left here, I have the updated version of the picture on today's leaflet. The one on today's leaflet was the very first image of this type, which caused huge excitement as we saw the shadow of the first black hole directly. And what's happening in these images is that somewhere in the center, there's a black hole. It's not quite all of this black, some smallish fraction of this dark spot is the actual black hole. And around the black hole, we have lots of hot dust and gas, which is swirling around quite violently, and which is very bright. And that's the thing we're seeing. And so we can see all this dust and gas swirling towards us, and the brightest part is where the gas is swirling towards us. And these fabulous details are made by also taking into account the polarization of the light. And the much fainter stuff behind us is when the light, this accretion disk of hot gas and matter, is trying to shine at us, but some of those light rays have to go around the black hole. So this first image was of a very, very big black hole. Oops, excuse me, a very, very big black hole in a galaxy very, very far away. And it just happens to be so bright that we can see it despite it being in a faraway galaxy. And more recently, we got another image. So going back to the black hole in our galaxy, the one that was whose existence was inferred by these stellar orbits in the first evidence. SAG star is the black hole in our very own galaxy. And we got a slightly more fuzzy image, but again, recognizable as having a pretty dark splodge in the center of it. And that's the black hole in our galaxy. So, okay, we know that black holes exist, or we're very confident that black holes exist. But what actually are they? So, black holes form when large stars run out of fuel and when they collapse under their own gravitational force. So they're too big to form a neutron star or a white dwarf or any other kind of possible state of a star when it runs out of the nuclear fuel in its core. And so you have this big fat star and it can't support itself by the nuclear reactions that it burns when it's shining. And it simply has to collapse under its own gravitational force. So all the gravity of all the parts of the star make it collapse in onto itself. And when the star is sufficiently big, and if it's too big to form a neutron star, it forms a black hole, and that for us is just a word to describe a totally collapsed object. In general relativity, a classical black hole is a region of space and time from which nothing can escape. So because it's collapsed down so dense, you can actually get this phenomenon whereby the light bending that we were talking about when Einstein's theory was first verified experimentally, or the first evidence supporting it was found experimentally, that light bending effect becomes so extreme that if a light ray would happen to try to escape the black hole, it just can't. It has no hope to. The force of gravity is so strong in aggregate that the light ray can't climb out. And so that's why it's black. Black or nearly black. We'll see that in a moment. So this outer extent of a black hole is known as the event horizon, and it's a surface from which nothing can escape. So not just light, but nothing. Why is that? Well, light, the speed of light, as you might know, is the ultimate speed limit on all forms of matter, to the best we know. So as far as we know, nothing can travel faster than light. And so if light can't escape from a black hole, then certainly you can't escape from a black hole either. So if you happen to be this astronaut in a spacesuit and you were tempted to find out what would happen if you jumped into a black hole, then unfortunately you would never be able to tell us about what happened when you fell in the black hole, because you're not coming out, at least not in the same form you went in. Deep inside a classical black hole, there's a singularity. What do we mean by singularity? Well, actually, it's just a fancy physics word to say that we don't actually know what happens there because our theory has broken down. It's a little bit like we asked our theory a question, and the answer it gave us was, well, I think the answer is 1 divided by 0. And 1 divided by 0 is a very strange thing because you can't divide by 0, as you might know. You can't divide by 0, and so the answer is meaningless, and that's what we call a singularity. So Einstein's general relativity predicts its own breakdown inside black holes, and our best theory of gravity just can't tell us what's really happening inside a black hole. And that means we need a better theory to describe the interior of a black hole. So according to general relativity, Einstein's theory, the region around the event horizon, so if we stay very far away from the singularity, which is somewhere deep inside the black hole, if we talk about just a relatively, hopefully, safer set of questions, we can ask, okay, even if we don't know how to describe the region very close to the singularity, can we at least talk about the horizon, the event horizon? Well, we can try to ask general relativity that question. And it tells us that the region around the event horizon is just empty space-time with low curvature, similar to, depending on the size of the black hole, if it's a big enough black hole, pretty similar to the kind of gravitational forces that we find on Earth, for instance, at the Large Hadron Collider. And okay, so as Nick was telling us, on Earth, on the surface of the Earth, gravity is fairly weak, and we can do quantum mechanics at the LHC without worrying too much about gravity. And that means that, okay, if we try to combine gravity, general relativity and quantum mechanics, then if quantum mechanics works at the LHC, which it does, then we should be able to study particles quantum mechanically around the event horizon, even if we don't have a complete theory of quantum gravity just yet. And that's quite a reasonable thing to try. However, it's also where things start to get delicate. Delicate meaning that famously, Stephen Hawking discovered in the mid-1970s that black holes are not quite black after all. Quantum mechanics predicts, when you study quantum mechanics around a classical black hole event horizon, it predicts that black holes radiate at a very low temperature, incredibly low, like such a low temperature that we would never hope to directly observe it. But it's not zero, it's in principle some very low temperature. And so black holes aren't quite black. They radiate, and this is known as Hawking radiation. Okay, fine, so good. What's the problem? Well, a little bit later, Hawking also told us that combining general relativity and quantum mechanics, we get a prediction for how this evaporation happens. And it predicts that black holes evaporate in a way that violates unitarity. And that's a problem, because unitarity was the basic ingredient of quantum mechanics that was just saying that probabilities have to add up to 100%. And so violating unitarity is a real big problem. And this is known, because it's such a big problem, we call it a paradox. It's known as the black hole information paradox. The deepest paradoxes in all of physics, and it remains unsolved to this day. It's called, in part, the word information is because the unitarity of quantum mechanics is linked not just to probabilities adding to 100%, but also to the information of the system we're studying being preserved in our description. And in some sense, what's underlying this violation of unitarity in those fancy words is saying that after something falls into a black hole, we seem to lose track of the information that was in what we threw into the black hole. When the black hole evaporates, we don't seem to be able to recover that information. Okay, well, Hawking's calculation was not a full quantum gravity calculation. He was combining general relativity, which is classical gravity, with a quantum mechanics description of other particles. So a natural question to ask is, if we do have a complete theory of quantum gravity, if we construct one in the present or in the near future, can it resolve the information paradox? And can it resolve the singularities that we find inside classical black holes? Well, one candidate quantum theory of gravity is known as string theory. String theory is a quantum theory, but it's not a theory of particles per se, it's a theory of strings and other extended objects. And the basic ingredients of the theory are that we have strings which are either open strings, like a kind of line-like strings with two endpoints. And in this cartoon, we have time going up at the on this axis up here, and space is in these two axes here. I believe this session is being recorded. There was a question there, so don't worry if your laptop runs out of battery. And then we also have closed strings here, which are closed loops of string. And it turns out the closed ones are the ones which describe gravity, but we usually have both types of strings depending on the string theory. So strings can be either closed loops or open with endpoints. And the basic idea is that different modes of vibration of the string on the microscopic level, when you zoom out slightly, the string looks very tiny, like a point. And these correspond to the different particles that we observe in elementary particle physics, in supposedly elementary particle physics. So the idea is that those particles are not quite elementary. If you look even closer into the microscopic scales, the idea is that they're made of one-dimensional strings. And we have interactions where strings can split and join, and this gives rise to the interactions in particle physics. Okay, so one of the things that made people very excited in the early days of string theory is that it seems, in almost all string theories, the theory automatically contains gravity. So it's a quantum theory of gravity by construction. And today and for many years, it has been the leading candidate for a theory of everything. So a theory of quantum mechanics, of all forces, and including gravity. And string theory has recently given us hints of a new description of the internal structure of black holes. And recent results in string theory suggest that quantum effects are important at the scale of the event horizon of black holes. And so a black hole, instead of being something in which everything has been crushed to a microscopic region deep inside, it may be more like a quantum ball of string, which we call a fuzzball. Fuzz means quantum, so fuzz is often used interchangeably with quantum, and then ball because it's a finite extended ball of string. String theory has also shown us how the information of black holes, or sometimes something we call the entropy. The entropy is a way we encode the amount of information, is beautifully encoded in a hologram outside the horizon. And in this cartoon, you see here that the information, which is represented again in binary digits, ones and zeros, is sort of painted on the event horizon in a form which seems quite holographic. And this idea is quite old, but it has been made very precise in string theory and has led to a huge amount of research over the last 25 years or so. So that leaves us with the question, well, what really happens if you fall into a black hole? In some way, when in an ultimate quantum theory of gravity, your information, the information in your body, in some description should be encoded in some kind of hologram on the black hole horizon or just outside the black hole horizon. But we really don't know the details, and there are lots of big questions here. And this is a really active field of ongoing research. And if we're very lucky, we might get some experimental insight into black hole internal structure in the coming years. So here I have those two cartoons for each of those more modern types of experiments. Here we have those two black holes that were spiraling in and just about to merge and ring down. And these waves that are coming out describe the gravitational waves, those ripples in the gravitational field, which we pick up in our detectors. And here again, we have, this one's a simulation, but an image of those radio telescope images of black holes out in the sky. So once we get more and more precise data from telescopes and from experiments, who knows, we might even get some insight into what's inside a black hole from experiments. So I'll wrap up. I think I'm going to finish slightly early, but hopefully that will give some time for questions and interactions. And please do ask me anything you like in the discussion session. And I'll just say that there are really many open puzzles in quantum gravity. And we certainly hope that maybe some of your generation will be the ones who solve them and explain them to the world. So I'll leave it there. Thanks for your attention. Okay, I think we
Thank
did
you
have
ever
a
so
question.
much. Thank you, David. Do we have?
Shall I take the questions?
Oh, you do it then.
I saw one in the chat, but I'm not sure if I can see the whole chat. Shall we take a few questions now before you want to stop the recording? Okay, everyone. Okay, Sophie asks, if quantum entanglement, okay, and Nick has a question, can I explain holography a bit more? Sure. Okay, so let me take Sophie's question first. If quantum entanglement is instantaneous, faster than light, can it theoretically escape a black hole? And then, is there any potential for imaging inside black holes using this? Well, that's two very, very good questions, Sophie. Thank you very much. So quantum entanglement is a quite delicate thing, which you know we have to be a little bit careful on what we say is instantaneous. So you know, it's impressive that you're already aware that there's some element of instantaneous, you know, immediate action when we have entangled particles, for instance. And if we make a, you know, the particles can be very well separated, but entangled in an entangled quantum state. So what that means is that if we perform an experiment which might change one of our particles, that change, according to quantum mechanics, instantaneously affects the other particle, but in such a way that although the action is instantaneous, we can't actually use that to send any real information faster than the speed of light. And so it's a nice idea, and people have thought about using quantum entanglement to somehow use that to get information out of a black hole. And actually, your question is surprisingly close to some ideas that people have been investigating just in the last couple of years in quantum black hole physics. And people have been trying to build some models which use quantum entanglement to try and somehow quantum teleport information out of a black hole. But I would say these ideas are kind of speculative, and they raise almost as many questions as they answer. So that's my answer to the first part. And the second part was, and then is there any potential for imaging inside black holes using this? Well, I think for the second part, that's really tricky because we don't know any way to actually image inside black holes, even using that. So even if we will be able to send some information, even if we could send some information, which we can't in principle, it will be extremely hard to try and set up an experiment. For instance, I don't know what exactly you have in mind, but you know, if you imagine imaging inside a black hole, I would think that you're trying to maybe shine a light deep inside the black hole and then try and use some kind of quantum entanglement trickery to get that some kind of information from that back outside. I think that's pretty much going to be impossible in our lifetimes. But very good questions. Thank you very much for them. Okay. I'll maybe focus more on the students' questions, Nick, if you don't mind, and I'll come back to holography at the end. And I'll just keep talking, and you can tell me when to stop when I should stop. But Alec asks, what's your opinion on Interstellar's depiction of black holes? I'm really happy I got that question. So anybody who's seen the film, I love the film, by the way, Interstellar. I think it's great. And if you haven't seen the film, and if you're interested in physics, you know, anything I talked about today, I really recommend this. You know, it's there's a certain element of Hollywood glamorization in it, but one of the things that one should definitely say in favor of what was achieved in Interstellar is that they worked a lot with theoretical physicists to really get the physics very, very good and accurate in terms of most of what they did. And so they used the help of physicists solving real equations to study what happens with a lot of things I didn't really talk about today, how time runs at different speeds in different parts of gravitational fields. So if you watch the film, you'll see that they play a lot with this the amount of time that is elapsed. And so, but let me answer the question, which is, what do I think of this image? I think it's fantastic. I think it's beautiful. I can tell you which part of the physics they kind of broke a little bit, and they deliberately kind of sexed it up in a Hollywood kind of thing, which is, if we compare the real ones, where was my real image? Here, these real images of these blobs. So this is what you would really kind of quote unquote see. Things would be maybe a little bit fuzzy. They'd be a lot brighter in the foreground, and a lot fainter and fuzzier around the back. If you were closer to the black hole, it would be less fuzzy than this. But I think coming back to the real picture, what we would see is that this big halo that they depict at the top and the bottom, this is quite exaggerated. And of course, they've done it to make it beautiful for the the big screen. And otherwise, the image is really brilliant. Is that they really used real physics equations going back papers quite a few decades ago of the swirling gas. So this part here is pretty accurate. This halo top and bottom, okay, maybe a little bit exaggerated, but overall, you have to say they did a really good job, I think, on the physics in that movie. Okay, Elliot and Drew ask, what are the conditions for the formation of a new black hole by a massive star rather than the formation of a neutron star? Okay, great question. And the simplest sort of answer in a nutshell is it's a question about the total mass of the original star which is collapsing. So the original star, when it collapses, it's quite a violent process, and in that process, a bunch of the mass gets sort of flown off out into outer space, and only some portion of the mass actually remains in the final object. And we've got to ask ourselves how much of that mass is left. And if I go back to my data about black holes, I can partly answer it, which is that the best way, to the best of our knowledge about neutron stars, they can exist, and these units are in solar masses. So one means the same mass as our sun, one solar mass. So neutron stars, as far as we know, can exist and be stable up to maybe 2 and a bit solar masses. We're not quite sure where the line is. But beyond 2 and a bit solar masses, a neutron star is going to collapse under its own gravity. And so, these things here, we're not entirely sure. People are slightly hedging their bets there. But for sure, if you make something, a big star collapse such that the final amount of mass is going to, let's say, be 5 solar masses or 10 or bigger, then the only thing we know that can support itself, or it didn't, in some sense support itself, or in some sense it's totally collapsed, depending on our description, is a black hole rather than a neutron star. Whereas if it's going to be 1 to 2 solar masses, it's most likely to settle down to a neutron star. Okay, thanks for the question. Okay, next one is from Eloise and Liam. How can you tell a black hole made out of antimatter from a black hole made out of matter? Well, the short answer is the black holes we've seen are made out of matter, and that's because in our universe, the dominant the dominant proportion of our universe by far is matter. There's this famous thing called the matter-antimatter asymmetry, and so antimatter is not present in our universe to the quantities that we could ever see a black hole made out of antimatter. But you may know that if you happen to have any kind of substantial amount of antimatter that would come into contact with some matter, then it would annihilate very quickly into energy. So thanks for the question. Henry asks, what effect do gravitational waves have on the structure of the vacuum? What actually are they, and how can they be detected? Yeah, very good question. So this is the part of the story that I didn't think I had time to tell, but maybe I could have had time to tell. So I'm happy you asked it, because I can try and tell it now. So I should use 2 pictures. So I want to mainly use this picture, but let me go back to this very first picture I had about the rubber sheet. So Einstein's gravity, Einstein's general relativity, describes gravity in terms of the curvature of space and time. And so what it tells us is that when we have a matter, it affects the curvature of space and time, it affects the shape of space and time. And space and time are also dynamical. They can change with time. For instance, if the star was moving, imagine a heavy ball rolling around some rubber sheet. It means that the actual shape and the relative stretchiness of space and time changes with time, can change with time according to the mass that's present. And so you should think of this space and time like kind of a stretchy material. And that means, what does it mean? It means that distances, each of these lines expresses distances as we will measure them between 2 points. It means distances between two objects can in principle slightly vary according to what's happening in the gravitational field. And those distances, when we come to a gravitational wave, so let me jump ahead to a gravitational wave. Where was it? Did I go past? No, at the end. Yeah, so when these two black holes are spiraling around each other, ready to merge, they're making these ripples in the gravitational field, which then go out and out and out and become weaker and weaker as they disperse. And they are such that by the time this wave gets to Earth, it's going to pretty much pass through all of Earth. But as it does so, distances are going to change by some incredibly tiny amount. Some amount that is fractions of distances, even in particle physics. And so how do we actually measure them? We measure them with really big lasers. So we get, there are these two main ones in America and other lasers around the world. What we do is we build a station which has two big lasers pointed at 90 degrees to each other. We call them the two laser arms. And each arm of the laser detector is 4 kilometers in length, 2.5 miles long. And at each end of the lasers, there are mirrors which bounce light back and forth, bounce these laser lights back and forth. And these lasers are so accurate and the mirrors are so well insulated from all the kind of vibrations of the Earth. They're suspended with, there's lots of insulation in there, that when a gravitational wave passes through, the mirrors slightly shake. They vibrate slightly in such a way that we can measure the change in separation between the two ends of the 4-kilometer laser arm. And that's how we pick up gravitational waves. They're incredibly weak, and it's an incredible feat of engineering. And it's really remarkable that we can do it. But and lots of people thought it might be impossible, but after many decades of work, we can now detect gravitational waves directly.